Okay, so I'm going to start with a little overview and the idea behind that, and Philipp will take it from there and explore more about height map generation. So with LidarScout, we were trying to make it possible to visualize massive point cloud data sets directly, instantly, without having to wait for pre-processing. So let's take a look at some of these data sets. Here we have a data set with 18 billion points from part of the coast of California. And here, doing the pre-processing in order to create the LOD structure takes about half an hour. Then we took a look at another data set, Gisborne from New Zealand. And this one already has about 260 billion points, and LOD construction here takes about 2 days. So if you just want to browse through your huge amounts of point clouds and take a quick look at something, maybe find a region of interest, you have to wait days just for individual data sets. So this is where LidarScout comes in. With LidarScout, we were able to drop these times down to from half an hour to about 2 seconds, or for Gisborne, from 2 days down to 35 seconds. And with this bit of a startup time, we can then explore these point cloud data sets in real time. So the way this works is actually fairly simple. So first of all, with direct out-of-core rendering, we mean that we don't do any pre-processing. We take the data as it is on disk. Therefore, we also don't need additional disk space, which can always be a bit tricky if you have these large amounts of point clouds data. And we do not compute level of detail structures. So yeah, the first thing we do is we simply have these massive point cloud files, and we do some coarse subsampling, some more or less uniform random sampling from the files from disk in order to quickly generate this overview data set. So here on the top right, we can then see the point cloud in its entirety, the entire extent, and this was loaded in just about 2 seconds. But of course, if we zoom in there, then we will have some kind of garbage. So on the bottom left here, just a couple of points, but we cannot really see what's going on here. So the next thing we do is then the height map reconstruction, where we approximate the height map. It gives us a much better idea of what's going on in this region here. And if you zoom in close enough, and the screenshot you are already close enough, then we start loading the full resolution point cloud data from the files. And that way you can already explore the entire point cloud up to the full resolution. So here's an example of what this overview looks like. So first we have this point cloud from disk. It takes about 90 gigabytes. And after dropping, it only takes about 2 seconds until we get this coarse overview of the entire point cloud. And previously it took about half an hour of pre-processing until we could kind of look at something like that here. Then let's take a look at the same thing, but from close up. If we drop the point cloud, then we quickly get this coarse subsample here. But from this close up, we can't really see anything here. We could make the points a little bigger, but it would still not give a good impression. So what we do now is we quickly create these height maps for the current viewpoint. So we prioritize to the viewpoint. And when we zoom in closer, then we load the full resolution point cloud data. So of course this has some limitations, so it's not going to replace pre-construction of level of details. Right now here we can look at the full resolution in the center, but we have a very coarse resolution around that. Still, it allows us to explore these data sets in a matter of seconds instead of hours or days. So yeah, and then you can move around a little bit. Okay. So one of the reasons why we made this was kind of for ourselves, because we have all of these huge data sets. And yeah, we want to be able to look at them directly without pre-processing, which also means this has to be possible with the industry standard file formats. And one of the widely used ones here for aerial LiDAR scans is LES. And LSE, the compressed counterpart. And especially LSE is very widely used. It compresses down to about 20 or 25% losslessly. So whenever you download huge, massive LiDAR data, it's either LSE or sometimes zip compressed LAS, which is really bad. Yeah, but with these two file formats here that are widely used, we also have AIBs, so they're bounding boxes, and these help us for rendering. When we zoom in closely, we have these bounding boxes here, and if some of them are large, if they're near the center of the screen, We can then figure out, okay, this part of the point class belongs to this file, so let's load this file here for the full resolution. So let's take a look at LAC. So basically, we've chosen LAC because that's what's widely used, and whatever works with LAC also works with any uncompressed format like LAS, PLY, or whatever. And the problem with LAC is it's compressed, so we cannot do full random access to any of the points here. But luckily, LAC is compressed in chunks of 50,000 points, which would still be a problem because just setting up creating the decompressors takes a lot of time. If you want to uncompress 250 kilobytes of points, you have to initialize state for 10 megabytes of decompressor. But again, luckily, it uses adaptive arithmetic compression, which means the first point in each chunk is uncompressed, and the further ones are then successively better and better compressed. So basically, this allows us to load a subsample of every 50,000 points from the scene in order to create this coarse overview. For San-Simeon, this allows us to load a subset of 300,000 points. And for Gisborne, this allows us to load a subset of around 5 million points. And especially 5 million points, so basically we start from an overview viewpoint when we drop this point clouds, and 5 million points is more than enough for an overview. So the next consideration here is the disk speed. So disks are usually optimized for sequential access, but now we're doing some random access all around the disk here in order to fetch the few uncompressed points. But with SSDs, modern PCIe 5 SSDs, they have a theoretical performance of around 1 million random reads per second. In practice, we got closer to about 200,000 because the standard C and C++ APIs, they're not made for random access. They have poor performance here, so we would have to use native file APIs in Windows or Linux. We didn't manage to do that yet. But still, 200,000 per second is fine for our use cases here. So yeah, for San-Simeon, it means in 2 seconds, we load these 300,000 points that we have access to. And for Gisborne, we have 5 million points that we have access to. So yeah, Philipp is now going to talk a little bit more about the height map reconstruction that we do in order to quickly kind of get a better impression for the whole point cloud, to fill the holes in there and also improve the quality.
Yeah. So hi everyone. As Markus mentioned, in this example we have roughly 330,000 points. So on top you can see if we would just rasterize those points, it's pretty sparse. If we make the points a bit larger so that it fills most gaps, then you get something like in the middle. And yeah, it's okay, but the height maps are better. You can see it even better in close-up. So on top it's very sparse. In the middle you have sort of a closed surface, but it's pretty noisy. So every tree can basically be some point. And on the bottom we have a slightly over-smoothed thing, but you can clearly see the structures of mountains, for example. Or here an example from the Morro rock. You can clearly see the rock in the height map case. So to get the whole reconstruction, we split the whole domain into patches. Every patch is 640 by 640 meters. So for the processing, we have 64 by 64 pixels, and that's already enough. Let's have a closer look at one of the patches. So we take the chunk points for the patch, but not only the chunk points on the patch itself. We need to take care of the boundaries so that adjacent height maps fit together. So we take all the chunk points in a region of 960 by 960 meters. So in principle, we have our scan data, then we get the chunk points, then there's a triangulation step, and then we create rough height maps and textures already with interpolation. So here it's nearest neighbor and linear interpolation, both for the heights and for the colors. We tried several things, but this variant works best. For example, just rasterizing the points didn't work at all. And then in the end, we get a refined height map and texture. And for the refinement, we use a small CNN. And yeah, for the CNN also, we tried several things. The first attempt was with something like PointNet, and it failed completely. It was quite slow and very bad. The next attempt was DCTNet. It's rather used for depth map estimation, so slightly adapted for our use case. And in this variant, we already got better results than linear interpolation. Then I thought, yeah, maybe I can get a very fast, small CNN, even if it might be a little bit worse. But actually, it turned out faster and better than DCTNet. So here's how it works. So as said, we have these 4 inputs, nearest neighbor and linear interpolation, both for heights and colors. Each of those goes into an encoder. The encoders are a few convolutional layers. Each outputs a feature vector. Then we concatenate the feature vectors and compress them further with fully connected layers. That's in 2 steps. So at the end of this merging step, we get again 1 feature vector, but for all the inputs. Then we have some decoders that produce some intermediate height maps and textures. And here we concatenate on top the inputs again, basically like a skip connection. But since it's concatenated, we have more size than we should have for the actual outputs, so it needs another compression. And in the end, we get our height maps and textures, so the 64 by 64 pixels. Here are some quality examples. So given the chunk points, you can see here the scan for reference. Here's, if we would just take the linear interpolation as we take for the input of the network, it would look like this. So very hard edges and discontinuities, not very nice. In principle, you could also use a cubic interpolation, but you see the very dark and bright spots. The reason is that it overshoots in many cases, and it even overshoots with the height. So there are some random 200-meter spikes in the landscape with cubic interpolation. Then there is high-quality splatting. The colors are pretty good, but it has blobby heights. And we also compared to sort of UNet, so that's adapted from the neural point-based graphics in our framework. It's pretty close to our results, but in some cases it distorts the colors. And the reason is likely that they have just 1 encoder for all the inputs, so they're basically mixing heights with colors. And here's ours in comparison. Good. So here is a video. Yeah. As shown before, we can just drag and drop. And within a second, it already starts. This is a Gisborne data set. So this was taken on Markus PC with a very strong GPU and SSD, but it also works on this laptop, we can show afterwards. Yeah, the laptop is not super strong, just has a 3070 in it. Yeah, you can see which tiles you actually, or you can jump to the tiles, you can quickly see outliers. So if you, well, in future work, you could just view the scan while it's scanning, so maybe stream it from the plane directly. And then you could already see outliers and tell the plane to return to some place. So, coming to the end, there are some limitations. So due to the random access requirement, it basically only works on SSD. You could probably run it on HDD, but it will be very slow. In future work, you could stream it from a server, maybe stream the chunk points or stream the height maps. So people wouldn't even need to download the full data before they know what they need. The network, as it is trained right now, is a little bit dependent on the point cloud density. So it's mostly adapted to the roughly 20 points per square meter of the California and Swiss data set that we used for training. It works also with higher resolutions like in photogrammetry data sets, but it oversmooths, so it doesn't really use the information that's given. And the best way to deal with that is likely to adapt the patch size to the point density. So meaning for photogrammetry data sets, we should use something like maybe 200 meters per patch. Then also future work, of course, we would like to deal with proper or with full 3D scans like city scans. But of course, height maps are not a good representation for this. And another interesting idea would be to use generative models to maybe get more structures in a couple of patches so that you can, for example, see clearly some larger streets or rivers. And we have presented LidarScout, a method for quickly exploring large point clouds. We go from the bounding boxes through chunk points and height maps to the actual scan data. And everything is online. You can already download the binary and try it yourself. Code and models are online. And thank you for your attention.
Thank you. We have time for more questions.
Great talk. So with the random access, for those who've lived through the days of 300 and 1200 baud modems, when JPEGs came through, they would have an interleaved format, obviously, so you've got an idea. Would you think of proposing a slight variation, pre-process your data so that it was then more friendly for your approach, so you didn't have to worry about the random access so much?
Yes, maybe Markus?
So the whole kind of premise here is that we do not do any pre-processing at all. So we take the data set as it is, as we basically get them from the distributors, from the industry, and work with what we get. So of course, with pre-processing, we can always make things better and faster, more suitable, but we try to avoid that.
I was just thinking you could add that in as a separate tool and just add one or more extension on and say, if you pre-processed it, then on the second time you ran it, it would be so much faster.
Okay, yeah, that could work out.
Great talk, thank you. Maybe some naive questions. You jump straight to machine learning. What if we just use splines to do height maps? Do you need machine learning here? Maybe naive questions.
No, it's a fair question. That was also a reason or a critical point in the reviews. Actually, we didn't look at splines. It should be possible. I would expect that they are somewhat close to the cubic quality, but maybe without overshooting. So yes, would be an interesting idea.
Okay, more questions? Yeah.
Hello, nice talk. You mentioned one of the limitations being 3D buildings and that kind of more complex shapes. Have you looked at all at how to adapt this model for those kind of shapes?
And what? Sorry.
Have you looked at how to adapt the model to work better with more complex 3D shapes like buildings?
Yeah, there are several ideas. So one idea would be to go more in the direction of the neural point-based graphics. So basically just predicting the current view instead of predicting geometry. Or another idea would be to maybe merge height maps with an implicit representation. So we could run some adapted marching cubes, for example. Or maybe go to something, don't know how it's called, like having a height map on every face of a box. Things like that. The critical point is probably to keep the model fast enough. And that means likely that we need to stick with the image-based approach and learning.
Okay, any more questions? Yes.
In your future work, you mentioned possibly using generative models to infill. What would the goal be? Because essentially these would hallucinate all the features. But I agree it's cool, but I guess what's the end desired result?
Maybe we can show a little bit in the video. We have this updating step. You can roughly see here, there's this blur region in the back. So that's how it comes from the chunk points and the prediction. And the not so blurry part here between the high resolution scan, that's updated. So after we have the high resolution data, we can basically fill every pixel with proper information. So this is already a very big step, and I think we could use this level of detail for the generative models. And this would be good enough, well, for 10 meter by 10 meter pixels that you can represent, let's say, houses, streets, things like this. And with the chunk points, it's just not enough information. So, of course, it will hallucinate a lot, but maybe it has a piece of river here, piece of river there. You could have a reasonable approximation from the model, I guess.
Yeah, also it might be more expensive to generate those pixels than compared to a small CNN or something lightweight, but yeah, cool idea.
Again, I would expect that it's time critical, so it needs to be a very small generative model, probably.
Yeah, like maybe SDXL Turbo or something older.
Great. So any final question? If not, oh, great.
Hello. My question is, this data, where is it stored? Did you stream it, or you kept it on external drive? Or like 2.4 terabytes is terribly large.
Yeah. We had all of this on an SSD, so fairly fast PCI 5 SSD that can load about 15 gigabytes per second, but in terms of random access, about 1.5 million, about 1 million random accesses per second. So there wasn't any streaming involved here.
Okay. And another question, did you use some graphics API for this, or you used CUDA?
This is in CUDA.
This is all done in CUDA.
Because, as mentioned before, I'm not smart enough for Vulkan, so CUDA is much easier. It's easier to draw a triangle in CUDA than in Vulkan.
Okay. All right. And one more thing. How did you decide which points to choose in the first, when you just load the whole thing just to visualize the overall picture?
And it was kind of imposed by the file format, because we can only load every 50,000 point, since these are the only ones that are not compressed. And this is also actually a bit wasteful because, of course, if you load 1 point, the SSD loads the entire 4 kilobyte sector. So we would have more data that we load from more points, but we would then have to decode that stuff, and that's simply way too expensive. So we just load every 50,000 point because that's what the file format allows us to do.
Okay, thank you very much.
One more note, we also tried putting the data sets on an external SSD. Then, yeah, of course, it's a bit slower through USB, but it works.
Okay, so I guess then we're perfectly on time to wrap this session up. Thank you all. Thanks our speakers again. And we have coffee